Now that we know the derivatives of the hyperbolic trig functions, we could ask about derivatives of their inverses. Now the way we're going to do this is just like the way we did it for other inverses. I'm going to say, okay, well, let's say y is the thing we want to find the derivative of. So let's say y in this case is the hyperbolic tangent. Then that would mean that the hyperbolic tangent, or the hyperbolic tangent of y is t. And so if y is the arctangent of t, then that would mean that the arctangent of y must be t. Okay, and then we just take the derivative of both sides with respect to t. We take the derivative of the outside, evaluate the inside, times the derivative of the inside. The derivative of the hyperbolic tangent is the secant squared. So we get the derivative of the outside, evaluate the inside, times the derivative of the inside, dy dt. That's actually what we're looking for, right? Because y is the hyperbolic tangent. We want to find its derivative. And the derivative of t with respect to t is 1. That tells us that dy dt is 1 over the secant squared. And we want to simplify that so that it's in terms of t if we can get it, because that will be nicer. Since y is a function of t, then dy dt, we ought to be able to write it as a function of t. There is a connection between the secant squared and the tangent squared, and we know that the tangent of y is t. Here's the connection. We know that if you take the cosine squared of a number and you subtract the sine squared of that same number, you get 1. So if you divide both sides of this identity by cosine squared divided by cosine squared would be 1. Sine squared divided by cosine squared would be the hyperbolic tangent squared, and 1 over cosine squared would be the secant squared. Now that's perfect because in our problem we have 1 over the secant squared, so really that's 1 over 1 minus the tangent squared. Okay, and we know that the tangent of y is t, so this is really dy dt equals 1 over 1 minus t squared. I could just replace this hyperbolic tangent of y with t, because the hyperbolic tangent of y is t. Great, so now we know the derivative of the hyperbolic tangent. It's 1 over 1 minus t squared. Let's do it for, we'll do the same thing for the hyperbolic cotangent. So we again start with y is the hyperbolic cotangent of t. Then the cotangent of y is t. We'll take the derivative. The derivative of the cotangent is the negative cosecant squared. So we get the derivative of the outside divided with the inside times the derivative of the inside. Because y is a function of t inside another function. So we take the derivative with respect to t. We're using the chain rule. The derivative of t with respect to t is 1. So dy dt, if I divide by negative cosecant squared, I'm going to tuck that negative up here and put cosecant squared y down here. Now this same identity, cosine squared minus sine squared equals 1, could give us a relationship between cotangent of y, which we know is t, and cosecant of y, which we need to find, or cosecant squared. If I divide both sides of our basic hyperbolic identity here by sine squared, I get that the cotangent squared of y, sine squared divided by sine squared would be 1, so minus 1, and 1 over sine squared would be cosecant squared of y. So I have a cosecant squared here, so I get negative 1 over the cotangent squared of y minus 1. That tells us that dy dt is negative 1 over, since the cotangent of y is t, that cotangent squared would be t squared minus 1. I notice that there's this negative upstairs. I could multiply top and bottom by a negative 1, and then I'd have 1 over negative 1 times t squared would make that negative, and negative 1 times this minus 1 would make it positive, so 1 minus t squared. That's kind of interesting. The derivative of the hyperbolic cotangent is the same as the derivative of the hyperbolic tangent. If we look at these, you might think, well, if two functions have the same derivative, are they the same function up to a constant or not? And the answer in this case is no, and it has to do with the domain of the hyperbolic tangent inverse versus the hyperbolic cotangent inverse. To explain why, let's just look at a graph of the hyperbolic tangent. So hyperbolic tangent, that's the function that this is the inverse of. The hyperbolic tangent would be the sine over the cosine. Now the sine has an e to the t minus e to the minus t over 2, and the cosine has an e to the t plus e to the minus t over 2. Since the numerator and denominator are each divided by 2, if I multiply top and bottom by 2, it will simplify to be this function. Now, we can see that in the long run, as t goes to infinity, as t goes to positive infinity, these two terms will fade, and we'll just have e to the t over e to the t, which is just 1. So in the long run, the graph of the hyperbolic tangent approaches 1 this way. We know it goes through the origin because if you take e to the 0 minus e to the minus 0, you have 1 minus 1. That's 0 up top. Now as you go backwards, as t goes to negative infinity, this term, the e to the t's, will fade, and you'll be left with negative e to the negative t over e to the negative t, which is negative 1. So as we go backwards, the hyperbolic tangent will approach negative 1. Now we can also, while we're at it, get the graph of the cotangent pretty easily, because the cotangent is 1 over the tangent. So the cotangent is equal to e to the t plus e to the minus t all over e to the t minus e to the minus t, or 1 over the tangent of t. Now, if you take 1 and you divide it by a big number, you get something small. If you take 1 and divide it by a small number, you get something big. So as we go out here, to figure out the cotangent, we're going to take the tangent, which is a little less than 1, and divide it into 1, which will give us a number a little bit more than 1. So the cotangent is going to be coming down to negative 1. As we go backwards here, though, as the inputs go towards 0, the values of the tangent get small, so the values of the cotangent are 1 divided by smaller and smaller. That's going to have a vertical asymptote there at 0. We get a similar picture over on this side, because we're dividing 1 by smaller and smaller negative numbers, and so we get negative infinity as we come back. So this is the graph of the cotangent. Now what we're interested in is actually the graphs of their inverses. To get the graphs of the inverses, what we do is we flip the x and y axis, because for an inverse function, the outputs are the inputs and the inputs are the outputs. So just the x and y axes get flipped. Now we have these two horizontal asymptotes at 1 and negative 1. So this horizontal asymptote, when it's flipped, becomes a vertical asymptote at 1, and the other horizontal asymptote at negative 1 becomes a vertical asymptote at negative 1. Then we can see the graph of the tangent inverse. If we flip the x and y axes for that, it looks something like this. And the graph of the cotangent inverse, let's see, if we flip this, it used to have a horizontal asymptote at 1, that's going to become a vertical asymptote, and this vertical asymptote at 0 is going to become the horizontal asymptote. So here's the graph of the cotangent inverse. We basically just switched inputs and outputs to get the function that goes the opposite way, and that just switched the x and y axes. So now here we have the graph of the cotangent inverse of t. Oh, this is strange. I don't know why I have a t here when that should be x. Okay, so there's the graph of the cotangent inverse. Now it only works, the cotangent inverse only works if the value that you're taking the cotangent inverse of is either greater than 1 or less than negative 1. One way to say that in this case, if we write it in terms of x, is that the absolute value of x has to be greater than 1. The what we have here is the inverse tangent, and it only works if the value of x is near 0. It can't be any more than 1 or less than 1. So this one, the arctangent, that only works if the absolute value of x is less than 1. Right? Think of the absolute value as measuring the distance from 0. So the absolute value of x being less than 1 means that that x is within 1 or less than 1 away from 0 there. So the two functions seem to have the same derivative, but they're not actually the same function because they don't have the same derivative in both places. If x is small, then the arc cotangent isn't defined at all. Or if x is big, bigger than 1 or less than negative 1, then the arc tangent isn't defined find anymore. So these two kind of complement each other in a way.